Now let's talk about the maximum work obtainable from two bodies at finite temperatures T1 and T2. Now let us look at this diagram in which we have two bodies at T1 and T2. So for the moment, let us not consider that we have a heat engine in between these two bodies. Okay, let's just assume that these two bodies are merely brought together into physical contact. Now when they are brought into physical contact like this, so this is body 1, okay, at T1, and this is body 2 at temperature T2. Now in this arrangement, the work output is 0. There is no work output. Okay, and the final temperature that you achieve is TF, and this is the maximum final temperature that you can achieve, which is the arithmetic mean of the two numbers. So this is something you should always remember, that when you just bring these two bodies into direct physical contact, there is no work output, and the final temperature achieved would be the maximum, and that is the arithmetic means of the two temperature values. Now if I put a heat engine between the two bodies which act as my thermal energy reservoirs, okay, now a part of the heat withdrawn from body 1, that is Q1, is converted into work, and the other part is rejected, which is Q2. Okay, now if I say that the lowest attainable final temperature, now this TF is the maximum value corresponding to 0 work, but now you have some work output. Okay, now if I say if the final temperature that is attained, that is T1 approaches TF and T2 also approaches TF, if TF is the, you can say, least value of final temperature, this means that the work that is obtained would be the maximum amount of work, isn't it? So the lowest attainable final temperature corresponds to the delivery of the largest possible amount of work, and is also associated with a reversible process, because the maximum work output can only be obtained in the case of a reversible process. Alright, and this also brings us to another conclusion, that the final temperature has to be the least attainable temperature in the system. Okay, now as the work is delivered by the heat engine, the temperature of body 1 will start to decrease, and the temperature of body 2 would start to increase. Okay, now when both the bodies attain the temperature TF, because T1 also approaches TF and T2 also approaches TF, and when both the bodies have the same temperature, the value of work becomes 0. Okay, so let us say the bodies remain at constant pressure, there is no change in pressure, and they undergo no change of phase. There is no change of phase as well for these two bodies. Okay, now let's find out the total heat that is withdrawn from this body at which is Q1. So Q1 is equal to let us say the heat capacity Cp and T1 minus Tf. So this is the heat lost by body 1. Now the total heat that is rejected to body 2 is Q2, isn't it? So we get Cp into Tf minus T2. So this is the heat absorbed, and this is the heat rejected. Alright, now the amount of total work done, if you remember, is W is equal to Q1 minus Q2. So you will have Cp into T1 plus T2 minus 2 times Tf. So this is an expression that you'll get. Now for the given values, if you have the given values of Cp, T1 and T2, so these are the given values, the amount of work that we get it is a function of the final temperature. Okay, so you can say for given values, so this is also a point from which you can get a question. So for the given values of T1, T2 and the specific heat capacity at constant pressure, the work obtained is a function of the final temperature Tf. Okay, so the work will be maximum when the value of Tf is minimum. So this is something you can say is a correlation between the two. So work is maximum if the final temperature obtained is minimum. Right, now for body 1, let's find out the entropy change. So for body 1, the entropy change would be delta S1, and the temperature changes from T1 to Tf, and this would be Cp dt upon T. We remember the previous calculation in the last video, and this would be equal to Cp into log Tf upon T1. Okay, and similarly the entropy change in the system 2 would be from T2 to Tf, and this will be Cp into dt upon T, and this is Cp log Tf upon T2, and we all know that Tf is a value which lies between T2 and T1. Okay, now if you look at the diagram, this is a heat engine which is operating in a cycle. Now because entropy is the property, so the entropy change of the fluid, okay, in the heat engine which is working in a cycle would be 0. So you can say that for a cyclic operation this is 0. Okay, and if you apply the entropy principle on this, you can say that delta S universe is greater than equal to 0, and this would mean that what is this? This is simply delta S1 plus delta S2, which is greater than equal to 0. You just put in the values of delta S1 and delta S2, and we would get Cp log Tf by T1 plus Cp log Tf by T2, and this is a positive value. Okay, so if you combine these two things, we will get Cp into log Tf square upon T1 T2, and it is greater than equal to 0. So this is a relation that we get for the total entropy change for the system. Now from this equation, okay, we can say that the Tf would be minimum. So for Tf to be minimum, because we are looking to find out the maximum work output, so for Tf to be minimum, all right, this value, this complete value has to be 0, because the least value is 0 and rest of the values are all greater than 0. So this becomes Cp log Tf square upon T1 T2. This has to be 0. Now from the product of two numbers, we can easily see that Cp cannot be 0. So the only conceivable value which is 0 is this value. So you can say that log of Tf square upon T1 T2, it's a value which is equal to 0. Now what is log 1? Log 1 is 0. So you can say that this value over here, Tf square upon T1 T2, this is equal to 1, because we know when you put 1 over here, it becomes 0. This means Tf is equal to under root T1 T2. So this is the least attainable temperature Tf, which will give us the maximum work output. And if you put this value of Tf in the expression which was this, okay, you can have the maximum value of W. So you will have, let's put this value over there. So we will have W max is equal to Cp into T1 plus T2 minus 2 into under root T1 T2. Okay, so if you manipulate this algebraically, this is nothing but Cp into under root T1 minus under root T2 whole square. So this is the maximum work that can be attained from a system with two bodies at finite temperatures T1 and T2. Okay, now this means the final temperature of the body, that is Tf, it can range from T1 plus T2 upon 2 to the value under root T1 into T2, because this is corresponding to 0 work and this corresponds to maximum work. So this is the range in which the final temperature can have its values, and this is the value of the maximum temperature that can be obtained. So I hope you understood this concept and the derivation and the explanation. Now in the next video we will talk about the maximum work obtainable from a finite body and a TER, that is a thermal energy reservoir.